Okay, good afternoon to everyone. First of all, let me thank the organizer for the invitation to this nice event. And today I'm presenting to you efficient quantum algorithm to simulate open system through a single environmental qubit. Probably might be a bit hardcore presentation, but I will try to convey as much as possible the main takeaways of the work. So we know that quantum computers promise to reshape the computational landscape for many applications, including those in the biomed sectors. And the power of these devices is because for most of these applications, what you can do is you can translate your problem to try to find the ground state, the lowest energy state of some Hamiltonian H. And this Hamiltonian actually might not correspond to a physical system. You only need to encode in this Hamiltonian the target optimal values. So we can view, in a sense, quantum computers as a general purpose algorithmic framework for quantum state preparation. The paradigmatic example of this are so-called variational quantum algorithms, in which you want to start with parameterized initial state with some chosen parameters. And then by exploiting the variational principle, you update the parameters such that you find the optimal state that with good accuracy gives you the lowest energy. So what you are actually doing is you are trying to explore with a unitary evolution a large Hilbert space, and you are trying to restrict this space to a subspace of optimal solutions. This approach is very promising, but in recent years, it has been proven to have a lot of limitations. The first regards the fact that there is the problem of an exponential cost for training. Basically, the landscape becomes flat, and this problem is usually referred as barren plateau, so you're not able to get down with the end. And the second problem is more related to the fact that you are trying to evolve this system as if it is closed, but actually your quantum computer is an open system, is interacting with all of its environment, and this causes noises, so corrupts what you want to do. And what is actually happening, this noise is introducing non-unitarity. So for this talk, again, I will focus on an alternative framework, starting from the observation that we can think of open quantum systems as an algorithmic tool. So what is open quantum systems? We have a system that is interacting with some environment, and we want to describe an effective action on the environment that gives the dynamics of the system. And this, of course, is an important framework in many physical systems, if not any. I mean, it's one could argue that no system is really closed in nature. And what the interesting thing about this is that you can think as if the environment is driving the system to some steady state. So similarly to variational quantum algorithms, for example, you are restricting the whole space to a subspace of possible solutions. And you can think of this as, for example, a simple example is cooling. So you have a system at high temperature, you couple the system with a large environment at low temperature, and the environment will pump out energy from the system. And this, in the end, will give you the correct steady state. So this observation is key in interpreting this framework as really a general purpose algorithmic framework for quantum state preparation. And now the problem becomes in this setup that you have to design an artificial environment that is able to drive your system to the correct steady states. But the advantage is that you are not introducing any variational parameters, and the procedure is just kind of automatic because your environment will pump out energy from the system. And moreover, I will not cover this in this talk, but what is very interesting to me is that for this approach is that in principle, since your quantum computer is actually open, maybe you can find ways to exploit the environment of the quantum computer, like actually engineering that environment to do what you want. But even though we are not interested in this for this talk, once you're able to actually derive what is the effective action of the environment that you want, and usually under standard assumption, you get an equation which is called the Limrad equation. This equation is for the density matrix of the system, and you have a term which is the ideal unitary evolution, and then you have another term that describes this effective action of the environment. Of course, then when you have this, the problem is how do I solve this? Because in general, it's a difficult task. So classically, it has an exponential scaling because the density matrix scales exponentially with the number of degrees of freedom of the system. So the idea is I can encode this problem on quantum computers, but the issues, let's say, are still that in general, the evolution dictated by this equation is non-unitary. So what you need to have is an efficient encoding of the environment, and then you cannot solve the equation. So you need approximate solution. So you want to have a suitable system-environment interaction. And in recent years, a lot of algorithms appeared in the literature, quantum algorithms, to tackle this problem. And in this talk, I will focus on what I will refer to as collision models, which is also well motivated by cooling. So how do we implement collision models on quantum computers? So the standard approach to do this is I take the system qubit, so where the encoding of my system is, and I add extra ancillary qubit to the system qubit that encode the environment. Then I can make a unitary interaction between these two. And finally, I introduce non-unitarity because in quantum computers, a lot of times we forget that we also have non-unitary primitives, which are measurement and reset. So I introduce non-unitarity on the system by measuring ancillary qubit, and then at each time step, I reset them back. So the problem in this approach, in how it is generally implemented, is that the number of ancillary qubit, of this extra qubit that you have to add, scales with the number of system qubits. And if you look at each time step, the solution that you are able to reproduce at the level of density matrix, so the update that you have, is just a first order approximation of the formal solution of the Limrad equation. And this is only valid if the time step that you choose is sufficiently small, which means that you are increasing a lot of the number of steps. So if we look at this in terms of quantum computational resources, what you have is an algorithm which requires a lot of qubits and which requires a lot of operations. And this is a problem in the near to mid-term, as was also pointed out before, because if we want to accelerate the usage of these devices, in the near to mid-term, we have to deal with the fact that we have a limited number of qubits and we can only perform a limited number of operations on them. So our proposal starts from the so-called quantum noise formalism, and I will show you how from this we end up with actually stochastic collision models, which in terms of these two things of the number of qubits and depth of the circuit is more efficient. So what is the quantum noise formalism? So you start with a so-called quantum stochastic unraveling of the Limrad equation, which is a stochastic equation, unitary and linear for a system plus environment state vector. And it is stochastic because you have this dB operator, which are the generalization to operators of classical linear processes. And what we mean by unraveling, we mean that if you start with a state which is factorized, so you have some initial state for the system and your environment is in the vacuum, then by taking the average over multiple realization of this equation here, which in this formalism here amounts to taking the trace over the environment, you get exactly the Limrad equation. So in this sense, the two are statistically equivalent. So if you want to compute average quantities, which is always the case in quantum mechanics, these two will give the same predictions. Now the problem, if we want to apply this formalism as it is that the environment in this case is a bath of harmonic oscillators, a reservoir of harmonic oscillators, which is in principle infinite dimensional. So the idea that we had is this environment into the simplest environment possible in terms of quantum computers, which is just a single qubit. And in order to do so, you also have to replace the bath operators with the lowering operators on the qubit times a classical linear increment. So with this substitution, you get this modified stochastic Schrödinger equation, which, when correctly taking the average over classical linear processes, reproduces all statistical properties of the noise, and also it is, again, statistically equivalent to the Limrad equation. The only difference now is that, in principle, you need to have that your state is actually factorized at all times. But if you think about collision model, this is what is effectively realized in a collision model, because at each time step, you are taking the extra qubit and you are resetting them to 0. No? So in this way, we can view this approach as a stochastic collision model. So we were able to solve this equation via perturbative techniques to get this operator n. And now you also see how this approach is working. So again, you want to go to a final total time t, you divide it in time steps, and then in each time step, you drive a unitary interaction with just a single qubit, but now the interaction is random. And if you average over multiple realization, you get the evolution that you want. The advantage in terms of resources is that you're always using a single ancillary qubit, so the width of the circuit is reduced. And also, if we look at the solution that you get in terms of the update of the density matrix in each time step, you have this kind of update, which is more accurate than the standard approach because it contains more term to order gamma delta t. So this means that we might take a larger time step to get the same target accuracy with respect to the standard approach. Of course, there is an overhead, which is the sampling overhead with respect to the standard approach, but we have shown that this is not a problem, because if you want to evaluate the statistical error on the evaluation of observables, this will not scale with the system size. It is just scaling on the number of realizations. And then we also are showing further results in which we prove that the number of gates that you actually need is polynomial, and so this algorithm is efficiently implementable on a quantum computer. So just as some results, we first focused on a single qubit where you have this Hamiltonian, and these are the Limrad operator. So what is the environment doing on this Hamiltonian? We decided to fix all the relevant parameters, and we kept delta T non-fixed. So what we did is we wanted to compare our approach with the standard approach in reproducing a target evolution, which in this case is the numerical solution of the Limblad equation. And thus, we computed for varying values of delta T, the trace distance between the corresponding density matrix. And you see that our approximation is always giving a better solution. Lower trace distance, of course, is better by orders of magnitude. And for example, if we want a time step that gives a trace distance of 10 to the minus 8 for our approach, you would need a delta T, which is here. And if you want roughly the same trace distance, with the standard approach, you need a delta T, which is here, which is 4 orders of magnitude lower, which means 4 orders of magnitude larger number of steps. And finally, we also studied how we can study energy transfer dynamics for molecular systems. We consider just a system of 2 molecules that are exchanging an interaction, where this is the Hamiltonian. We decide that this is the dissipator, and we computed, again, numerically the evolution given by the Limblad equation, and we compare it with our algorithm. So I will just conclude by saying that in this talk, I try to convey to you the idea that the framework of open quantum systems could actually be exploited to prepare target quantum states. But if you want to stay in this setup, then you need to have efficient quantum algorithms to solve for the open system dynamics. And in our work, we have shown that we developed an algorithm, which is a stochastic collision models. And in this sense, you don't need variational parameters. You are reducing the number of qubits to encode the environment, and you have a better approximate solution in each time step. So it would be very interesting to apply actually this framework to large-scale molecular simulation and optimizations in system biology. And with this, I would like to thank you for your attention.
Thank you, Michele. And Fenglao, send me around if you want to do questions. You're the timer.
Sure. Thank you, Dr. Michele. So we have time for one question.
Thanks for the talk. Can you give some intuition on how you can use OQS to find the ground states of like any arbitrary Hamiltonian that you were showing earlier in your first slide with like when you replace VQAs with this essentially?
Yeah, essentially the idea is really to try to design your environment such that when you get this equation, it drives you to the steady state, the correct steady state. And the idea behind is that of cooling, basically. So you want something that is taking out energy from the system. So you want an effective term here that is taking down the energy. So that's the intuition behind it. Okay,
thank you, Dr. Michele. Our